Hi, and welcome to this video. Today we're going to be answering a few questions. I receive a lot of questions and some just don't require a full video. So I grouped a lot of them together, well, some of them together, and we're going to run through them in this video. And the first has to do with gears, and it's a question I received from Lee. Now, before we get into answering Lee's question, gears, I don't like to say they're complex, because when you say that, you scare people off. They aren't really that complex, but you have to wrap your mind around the basic principles. So if you want to learn more about gears than what we're going to look at quickly here, well, there's a link to a video I produced some years ago that sort of runs through the basics of how to produce gears, but also what all the different parts and teeth and ratio and all that stuff, how that works. So you can take a look at that if you want. For us, we're going to answer Lee's question, and Lee wants to know about gear ratios, especially when we have gears on the same shaft, compared to gears end to end, or side to side, or teeth to teeth. So let's take a look at that. So Lee, I have 3 examples here, and I really hope that this is what you were looking for as far as information goes. Now, the first is a straight up gear to gear relation, and I have 2 gears. One gear, the blue one, because of the red arrow that I've drawn on it, is the driver gear, the one that is driven by the motor. And the red one here with the arrow underneath is the driven gear. Now, if we look at this and we remember, everything in gears is proportional. So if one gear is twice the size of the other, well, the relation is going to be 2 to 1. If one gear has twice the amount of teeth as the other, we're going to have the same relation, and so on and so forth. Everything is proportional. That means that if I have a 2-inch diameter gear here, and a 1-inch diameter gear here, and this 2-inch diameter gear turns 1 full turn, well, this 1-inch diameter gear is going to turn 2 turns. 2 turns of the driven for 1 turn of the driver. And that, well, we can wrap our minds around that pretty simply because, hey, it makes sense. But what if I add gears to that? And look, I have the same gear, and it's the driven gear, and it's driving the same gear. So I know that relation, and I know that this smaller gear is going to be turning twice as fast as the larger gear. Okay, it's connected to a large gear, the same size as the first. What's that going to do? It's going to annul any advantage that I had here. This gear and this gear are going to be turning at the same speed. And this middle gear, well, just becomes an idler. Push one step further. This large gear turns this gear. I come back to my ratio, which is 2 turns to 1. So 2 turns of the red one to 1 turn of the blue. Or we can just cut those out and say 2 turns of this red one for 1 turn of the blue. Because these 2 intermediate gears, we call them idlers. They serve no purpose except for gapping the space between the 2 end gears. And let's push it further. We go to this last gear. And this last gear is going to bring everything back to 1 to 1. It's going to annul the advantage again. So 1 turn of this gear is going to equal 1 turn of that gear. This is a 1 to 2. This is a 1 to 1. And that's an important notion. With gear trains, with gears that aren't on the same shaft, all gears in between the first and the last gear are idler gears, and they serve no purpose other than to bridge the gap. So that's an important note. Sorry, I'm doing the editing on this video, and I realize that the sequence that we're in lasts 8 minutes. That's way too long. I'm starting to get worried that we might lose our good friend Jim up in Greenland, who tends to nod off after a while. So I think we need a little interlude. So let's go take a look at my niece's crazy dog, Dude, who for some reason doesn't seem to like to get his back paws wet. Let's get back to our video, Notion. If we look at the third example here, I flipped things around just because I drew it backwards. I have my driver gear here, and it drives a small gear, the same one there. We know what that ratio is. This blue gear to this small gear is going to be 1 turn to 2 turns. But there's a difference here. We've fixed another large gear on the same shaft as this small gear. They're both fixed on the shaft. And that means that if this small gear turns 2 turns, this larger gear is going to turn 2 turns. They're on the same shaft. That means that this large gear turns this small gear, turns this large gear at the same time. It's like we link the 2 large gears through the small gear, and we change the ratio. So we have 1 turn to 2, and we come back again. Large gear, small gear, and we again have 1 turn to 2, but we don't, because we have 1 turn to 2, 2 turns to 4 with the same ratio, but we're at an advantage of 1 to 2 and 1 to 2, so that means 1 to 4, and that's my advantage, 1 to 4. Now we notice that I get a much greater advantage, and I use a lot less space. Now these don't have to be in a straight line. I can shorten things up by offsetting some gears here and taking less space. But when we get right down to it, this occupies a lot less space and really gives me a great mechanical advantage. This, well, I end up with no advantage. This has a basic 1 to 2 advantage. So that's the function of these things. Now, there's something you need to notice here. I put the direction of rotation down. If we look here, the driver is turning in that direction, that direction, that direction. They're all turning the same way. But I notice on the first example that my second gear is turning in the opposite direction. I check on the second example and I notice that my last gear is turning in the same direction as the first. And I check on this gear assembly and I see that my drive gear and my driven gear are turning in the same direction. And why is that? Well, it's another basic principle, and that is that in a gear train, even numbers of gears reverse the direction of rotation, and odd numbers of gears, well, maintain the direction of rotation. Now you're going to say, I only have 3 gears here. Well, actually I have 4. What's going on? Why am I maintaining the direction? When you have a gear train, if you have 2 gears mounted on the same shaft and you're going through that shaft to drive the last gear, well, the 2 gears in the center, seen as they're turning together, well, they count only as 1 gear. So opposite direction, even number of gears. Same direction of rotation, odd number of gears. And that is what we exploit quite often when we have examples as a gear reverses on lathes. And all we're doing when we reverse the direction of rotation on a mill or on a lathe using a gear, well, is we're adding an extra gear to the mix, thus changing from odd to even or the reverse depending on what you're doing. So Lee, I hope that answers your question. Now, don't forget, you can go check out the gear video if you want to learn more about gears. So, let's move on to our next question. That really isn't a question. Someone posted in our Facebook group a picture of a part that was turned to a very small diameter. And actually it was stepped down to a small diameter. A very nice part. and the person got it right down to somewhere around, I think it was 0.15 millimeters. I'm not quite sure about that, but very small. And as it should be, I received a few questions about how to turn such a small part. Now I can't get that small here. My old lathe is pretty loose and sloppy, but I can get pretty small. So we're going to go take a look at how to approach the problem of turning a very small diameter. You're going to start with a tool that has quite a small tool nose radius. You also want a tool that has a good back rake and a good side rake. That will help to draw the chip away from the surface of the part. I'm also going to want a slow feed, and on my machine here, about 4/1000ths of an inch is as slow as it goes. I'm going to mount the tool so that the cutting tip is exactly on the axis of rotation of the part, height-wise. Very important. And since with this technique, the cutting edge of the tool is going to form the shoulder of the part, I'm going to want that edge to be very perpendicular to the axis of rotation of the part. For this demonstration, we're going to be turning 4 different diameters, each diameter being about 1/4 of an inch in length. First diameter is going to be 25/1000ths of an inch. Second, 50/1000ths of an inch. The third, 100/1000ths of an inch. And the fourth, 200/1000ths of an inch. The material we're cutting here is half hard brass. And note that the diameter of the part that I'm starting with is 1/2 inch. Knowing that the largest diameter I'm going to turn here is 200/1000ths of an inch, it may seem excessive to start with a 500/1000ths of an inch part. I mean, that's 300 too much. But there's 2 reasons why I'm starting with that 1/2 inch part. The first, well, is that I had a piece of 1/2 inch stock kicking around. And the second, well, is that I want to maintain a maximum of rigidity throughout the machining process. Now we're going to start a little counterintuitively, because most people would start by turning the 200/1000ths of an inch diameter full length and then work down to the 100/1000, then work down, and so on and so forth. But that is a problem, because that means that when it comes time to turn that final 25/1000ths of an inch diameter on the end, my whole part will be at its maximum of flexibility. I want to maintain rigidity here, and for that I'm going to start by turning the 25/1000ths of an inch end first, completely finished. Then I'm going to move on to the 50/1000, then I'm going to move on to the 100/1000, and finally the 200/1000ths of an inch. And that will maintain a maximum of rigidity throughout the machining process. So I'm going to want to turn the small diameter first, but there's a problem with that. I can't just cut it in one foul swoop. Now why is that? Well, the chip is going to be quite wide. Now I can give all the back rake that I want. A chip that wide is going to have one edge much longer than the other. I mean, the edge that's going to be on the 1/2 inch diameter side and the edge that's going to be on the 25/1000ths of an inch side are going to be very, very different in length. And that means that the tool can draw the chip away as it curls off of the part, but the difference in length is going to flip the chip over onto the surface that I've just produced. And since the diameter that I'm producing, the 25/1000ths of an inch, is quite delicate, well, that chip that's flipping over could very well push that diameter off its axis. So what am I going to do? Well, I'm going to take successive cuts, but I'm going to be very careful not to leave just a small cut at the end. We're not going to be doing a finishing cut here. We want the part to be reasonably rigid when I take that last cut. Now, as you may know, I'm lazy. And that means that I don't like to make things complicated. Now, my part is a 1/2 inch. I want to touch off the outside diameter. and then start from there, setting my 0 on that outside diameter. And that's fine, but my part is nice and round and accurate, but it's in a 3-jaw chuck, so it might be turning a little off axis. And if that's the case, what most people will do is take a few passes until they get a complete diameter, and they'll start from there. But by that time, they're somewhere around, let's say, 498 thousandths of an inch. They're not at a ½ inch, a nice number I can remember that's easy to count from. So what can you do? Well, you don't have to create a full surface. If you take your first pass to set up your 0 on a part that you know measures the right diameter and it's a little offset, if you take successive cuts until you touch just half of the diameter of the part, just half machine, not the other half, well, that means that where the two halves meet on each side, that is exactly ½ inch, and that's your 0 to start out with. So if I touch off here and I realize that I do have a little eccentricity, that's what I'm going to do. So I've turned my 25 thousandths of an inch diameter. Next one, well, is going to be 50 thousandths of an inch because I'm going to double each step. So 25, 50, 100, and 200. I don't have to reset my 0 here because I didn't change the graduated collar's position. All I have to do is back up past my original 0 and plunge in towards it, just to take away any backlash that there is. And on this old lathe, there is a lot of backlash. So once I get back to my original 0, well, I'm going to plunge in progressively to get to my 50 thousandths of an inch diameter. How am I going to do that? Well, from 0, I'm going to plunge in several passes, well, at least 3, and I'm going to cut at a depth of 225 thousandths. Now my machine cuts on the radius, so 225 on one side, and since the lathe is turning, 225 on the other side. That gives 450, and that will leave 50 thousandths of an inch for the diameter that I'm producing. Then I'll move on and use the same approach for the 100 and the 200. So let's blast through those operations. There you go. 25 thousandths of an inch, it's equivalent to the width of 8 human hairs. So we're starting to get pretty small here. Now, let's move on to our next question. The last question was brought to me by Robert. And Robert is having a hard time wrapping his mind around the whole notion of threads, pitches, number of threads per inch, and all that jazz. If I say that I have a screw that is 1/4 20, so it's an imperial screw, and it has a 1/4 inch major diameter, and it has 20 threads per inch, well, the pitch of that thread is not 20. The pitch is how far a thread advances axially in one turn. So if I turn a 1/4 20 screw one full turn, it will not advance 20. 20 isn't a dimension, it's a number. What it is actually is the number of threads in 1 inch. Let's use the lead screw on this milling machine as an example. Here I have a graduated collar, and we can see that it starts at 0 and it goes all the way around to 0.9 and finally comes back to 0. And that means that one full turn here is equal to 0.1 inches, 100 thousandths of an inch. And when I lock it onto the lead screw, my lead screw under here is somewhere around a 3/4 diameter lead screw. Once it's locked on and we turn it one full turn, well, we can see that the graduated scale and the lead screw and the table have advanced by 0.1 inches. The pitch of this thread is 0.1 inches. What's its description? Well, its description will be a 3/4 of an inch, that's its diameter, 10 acme thread. Why 3/4 10? Because in imperial, a thread is described by its major diameter and its number of threads per inch. This lead screw has a pitch of 0.1 because its pitch is 1 inch divided by the number of threads per inch. So 1 divided by 10, that means the pitch is 0.1. And I can see that clearly here. One full turn is 0.1. So the lead screw here is a 3/4 10 acme screw, and its pitch is 0.1. But what about our 1/4 20 thread we mentioned earlier? Again, 1/4 major diameter, 20 number of threads per inch, not the pitch. The pitch is 1 inch divided by 20. Because there's 20 threads in 1 inch, and 1 divided by 20 is 0.05. So 50 thousandths of an inch is the pitch of a 1/4 20 screw. Part of the confusion comes from the metric system, or vice versa, depending on which direction you're looking at the problem. In metric, there isn't the calculation of pitch that we have in the imperial. It's much less confusing. But because the two systems are different, it is confusing. What do I mean? Let's say I have a M10 by 1.5 thread. 10 is the major diameter. 1.5 is the actual pitch. They don't give you the number of threads per millimeter in the metric system. They give you the number of millimeters per thread. They've already figured it out. You don't have to backtrack like you do in the imperial system. So if you have a 1/4 20 thread, imperial, your pitch is 0.05. If you have an M10 by 1.5 thread in metric, your pitch is 1.5. There's no division required there. I hope this clarifies things for you. And if it doesn't, well, you can go and check out my threading on the lathe video. It could help you with that. Now, that is about all the questions we're going to attack today. There's more, so there'll be more of these Q&A videos coming. But until we meet again, as usual, have fun, be safe, and happy machining.